Sorry, back to me, excuse me. Back to me. I wanted to remind you of something from yesterday. That carbon gets shuffled between living things in the atmosphere here, between living things and other living things in decomposition. We haven't even touched on carbon moving in water. We'll do that later. But something I said yesterday that I want to make sure I say more clearly today. Nice move, Dylan. That's for you. What I wanted to say with more clarity yesterday is that it's a very rare, unusual circumstance where carbon becomes rock anywhere on the planet. That's not that common. If you think about it, you're trying to get organic material sandwiched in rock. And because rock accumulates slowly, like at the bottom of the ocean, if you drop a little bit of sand, the worms will still find the edible stuff. So these are really weird flukes, but in your lifetime, you have experienced one of them. Like when we have a really big fire that denudes our hillsides, followed by a really tremendous rain, and a whole bunch of soil erodes from the mountains and piles up out of the river mouths into the ocean. You know, if nothing mixes up that sand, that could become a small fossil fuel deposit in a few gazillion years. Think about it. There's probably some decomposing stuff at the bottom of the ocean, and then anybody know what those numbers were? Like 48 million dump trucks of sand come out of Sycamore Creek Rivermouth all of a sudden? That might be enough sand to pile up over some organic material that was there before the storm. Now there's carbon bonds that can't get cycled back into life. Now they're buried deep enough where that will eventually compress into rock and squeeze those organics into fossil fuel. You have, in your lifetime, a sometimes painfully personal, local, recent memory of one of these otherwise rare events. You saw one of these, where organic material gets buried under enough stuff that might eventually become rock. I've seen a few, not in person, but I was alive when there was a big tsunami that hit, I think, Indonesia or something. Does anybody remember where that was, where Phnom Penh is? Anybody know how to say that correctly? There's like a really well-known tourist destination, some really fancy beach. They made a movie out of this with Naomi Watts, where like a family is tossed around this resort community by a tidal wave.
Oh, yeah. I definitely remember, I just don't remember where it is exactly.
All right, so details aside, imagine when that tidal wave water recedes back out to the ocean, that's dumping a gazillion dump trucks worth of sand all over some coral reef out there. That could take some organic stuff and trap it deep enough that decomposers can't reach it. That will become fossil fuels one day. These are rare events. In other words, please look up, this is a trickle of our planet's total carbon on an annual basis. It's just a little tiny dribble of our living carbon that ends up stuffed into some rock. Just a teeny smidge. And you know, rocks don't erode that quickly. Volcanoes don't go off that often. But you know, every now and then, a little bit of rock carbon erodes from a rock or gets spat out by a volcano. That's another trickle. See, this is a trickle too. There's just a little bit of carbon becoming rocks and just a little bit of carbon leaving the rocks, except for our modern economy. This is debatably the single biggest thing humans have ever done to the planet. everything in our modern world, all the countries of the world, our economy relies on digging up rock carbon, ancient, buried, leakage carbon. We're digging it up all over the planet, and we're burning it to make energy, and that's making CO2, all at once. All of our coal, our natural gas, our petroleum. All the airplanes, all the tanker ships, all the trains, trucks, all that stuff. All the electricity, all the fancy factories that build the flat screen, factory that mined the, or squeezed the rubber, whatever, to make my stupid shoes. Our whole world, the entire modern economy is all a part of this. We're taking rock carbon and we are flooding it into the atmosphere. There's a bunch of ways that we can measure the history of carbon in our atmosphere. So we can go back in the fossil record and give you some pretty accurate estimates on what carbon levels were years ago, decades ago, centuries ago, millennia ago, even millions of years ago. We can give you pretty good estimates. And there is no time in our history that carbon has changed this quickly. We've basically doubled our carbon in 150 years. That's a really, really big change. Yeah.
So if we weren't to extract it and we were to just like leave it in the ground and not burn it, then it would be completely fine for the environment. I mean, it's just this small portion, but it's the fact that we're like digging it up and burning it and like.
Yeah, so I mean, it would neither be good nor bad for the environment, but the amount of carbon that becomes rock is probably the same as the amount of rock that is dissolving, because at any given time our planet has the same rock, right? Rock is just a slab smashing into another slab, so there's new rock coming up and old rock going down at all times. So globally, these are not, it's like what you call a steady state equilibrium. Like the amount being lost and the amount coming back into play are probably on average about equal. At any single moment, you might say like, oh, we just buried a whole bunch, or oh, a volcano just went off. But over decades or centuries, these are going to cancel out. What we've done is we've accelerated 1/2 of that. Okay. I wanted to review what we had done yesterday, but I don't even want to talk about carbon, and I'm leaving the water carbon stuff for later. Anybody want to ask me anything about what I just said? Because I do need to talk to you about nitrogen. This is really intimidating. I want to warn you that you don't have to explain actual chemical reactions. Please look up. There is no chemical reaction here. Hold on. There's a bunch of bacteria that have really complicated lives, and in those lives, they absorb one nitrogen thing and give off another nitrogen thing. That's like, you all realize that you drink water and you make pee. That's not your whole life, and that's not a chemical reaction. That's just an input and an output. So there's a whole bacterial ecosystem underground, and each of those different species has a different diet. They have their own hobbies. They like their own music. And all those different bacteria, they have inputs of nitrogen and outputs of nitrogen. It's just part of that ecosystem that this happens or this happens. So these aren't chemical reactions. You don't have any chemistry here. You just have chemicals in and chemicals out. This is not chemistry. It's like water in, pee out, input and output. What was your question?
No, just continue. It was about that.
Oh, you want to hit it really quick?
Yeah. So the carbon, that it's like with the organic material, the fossil fuels, that's living matter that got not broken off, but living matter that got trapped and now turned into fossil fuels. Makes sense?
Yeah. So it used to be living. It was trapped in rock. So instead of getting recycled into more life, it just got squeezed into rock stuff. That's what fossil fuel does. Okay, here we go. First of all, I've color-coded this. If yours is not color-coded, you could use little asterisks or stars or circles and underlines. But please look up. Red is bacteria. So here's a bacteria, here's a bacteria, there's a bacteria, here's a bacteria, and there's a bacteria. Those red colors, that's only where you have a specific bacteria. You know, you can think of these as like individual parts of a complicated system. They have all sorts of stuff that they eat and all sorts of chemistry that happens in each of these bacteria. This is just one of their inputs and one of their outputs. All of this, please look up, all steps in this cycle are done by bacteria. So as part of being that one bacteria, they make these transformations. Those are in blue. Please look up. That's just input and output as part of their metabolism. It's not the whole thing. It's not a chemical reaction. It's just one of their inputs, one of their outputs. Like water in and pee out, like this. That's blue. Those are transformations of nitrogen. So somewhere in that bacteria, they just change the nitrogen compounds. This is part of their life. And finally, if you had to do this on an AP test, and you like forgot but wanted to give yourself a hint, notice that the shape is like a bubble letter lowercase n, as if you had just traced a line around a lowercase n. So watch me. Atmosphere, underground, above ground, underground, above ground. It's like you're tracing a bubble letter n. That might help you someday if you had to explain these things on an AP exam. I want to start with gas, and we're going to follow around this way, but there's no like starting point or finish point. Also, you notice there's no rock cycle here. Nitrogen never becomes rocks. Those rocks never dissolve to make nitrogen cycle. This is just atmosphere to life to atmosphere to life to atmosphere to life. Okay? I'd like everybody to take a breath and hold it. It'll be about a minute. On your marks, get set. Hold it. Now, your lungs right now are 71% nitrogen. It is the majority of the air. And all of us need nitrogen. It's one of the most important nutrients in your entire body. You use it to build all your proteins, but please breathe out. You just let go of all that nitrogen. You need it, but you can't breathe it. That's called atmospheric or molecular nitrogen gas. It's the most common part of the atmosphere. It's a diatomic gas, so it's a buddy system. Two atoms are always holding hands. Like O2 is oxygen, or H2 is hydrogen. If you speak chemistry, the Hofbrinkel elements, the diatomic gases, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine are Hofbrinkel acronym. Oh. And these are gases that are in a buddy system. Like when little children go walking in the park, they're supposed to hold hands with another little human so they don't get lost in the woods. Nitrogen gas is useless to most life on Earth. All life on Earth uses nitrogen. I'm pretty sure there is no living thing on this planet that doesn't have nitrogen. But none of us can use nitrogen gas except for one small category of organisms. And they don't even do this for the nitrogen. They do this as a waste product to get rid of hydrogens. They're called nitrogen-fixing bacteria. They live in soil, water, and inside these structures of roots called root nodules. You have to know all this. Root nodules. They live in soil, they live in water, and they live in root nodules. I don't know if you need to know this or not. Every science dork on the planet knows that these are called Nitrobacter species, but I don't know if the College Board has ever asked that. That's the name of nitrogen-fixing bacteria. They're called Nitrobacter bacteria. And they do this neat trick. Please look up. They do this thing called nitrogen fixation. They make nitrogen that's useful to life. They transform nitrogen gas, useless, into ammonium, which is very useful. That's the #1 plant food. I slipped in a vocab term that I'm guessing most of you didn't write. A fixed element is in a compound where it's useful to life. Watch. This is free nitrogen or abiotic nitrogen or nitrogen gas. This is called fixed because now life can absorb that. You can't metabolize nitrogen gas. Neither can a plant. But a plant can absorb ammonium. So it's fixed. It's useful to life.
Is that just a term for nitrogen? Or is that like...
No, thanks for asking. You can fix carbon.
Okay.
So we would say that this is fixed carbon. Like now it's useful compound. BT dubs. I've only heard this used for nitrogen, but I know that it's a general term. So ammonium is the most important plant food. It's the majority of plant fertilizer worldwide. It's the cheapest fertilizer probably. Have any of you heard of a domestic terrorist named Timothy McVeigh, who many years ago in Oklahoma built a bomb inside of a van and parked it at a federal building and killed a bunch of FBI employees because he hated the government?
Children.
What's that?
It was in front of a daycare too.
Oh, really? I didn't remember that. I'm sorry. Yeah, totally creepy bro. He made one of the cheapest bombs because he just filled his van with fertilizer. He just went to like an ag warehouse and bought like, I don't know, 40 bags of ammonium fertilizer. It was like $200, super cheap. He did some fancy chemistry that I don't understand, and he set a timer and it blew up and caused great harm. That was this, the most common, one of the cheapest plant fertilizers. All plants use this. Plants use ammonium to build amino acids, and I feel like all my students know this because in health or nutrition or in bio you learned this. If you stick together a bunch of amino acids, you get a protein. How many of you knew that proteins are assembled from amino acids? Tight. If you didn't know, I treat that as an assumption. Make sure you write that down. Amino acids are the building blocks of protein. There's a detail down here that I got to talk about. I told you before, nitrogen-fixing bacteria are found in soil and in water and in root nodules of plants. Please look up. there's a nitrogen-fixing bacteria, and there's a nitrogen-fixing bacteria. They exist in the soil. But look at this plant. It has these little bubbles in the roots that house the bacteria. They're visible with the naked eye. They look like little pellets of styrofoam. Has anybody ever broken styrofoam? And you get those little tiny pellets that cling to you with static, and you like can't shake them off because they like stick to other places, and it's really infuriating. When I was a little boy, I snorted one of those by accident. By the way. Got stuck in my nose. I had to go to the emergency room. I've been dumb since I was little. Why am I dumb? I hit my head a lot, I think. Yeah. I was probably dropped as a baby.
Like, why did you snort it? He's dumb.
Kids do such weird things.
I really can't recall, but like, you know how your memories get so faint if they're distant that you start to build stuff around them? If I was forced to take a guess, I would think a homie and I were messing around and we like either dared each other or tried to see if we could.
Dude, remember when we snorted Fun Day?
Yeah.
That was gnarly.
That's not bad.
I snorted over this thing.
Okay. Back to me. Those root nodules on a plant look like little pellets of styrofoam. You can see them with the naked eye. You can kind of crush them. They're sort of soft. And they're like a home for this bacteria. Do you all know that some plants have more protein than others?
Yes.
Like, what's a vegan or vegetarian supposed to eat for the protein?
Like peanuts?
Soy.
Beans.
Like
Nuts,
lentils.
beans, legumes. That's right. Now get this. Some plants have just enough protein to be lettuce, low protein. Some plants have like hella protein. Like soybeans, black beans, nuts, lentils, or whatever. Now, if you need a lot of amino acids, you probably are going to need a bunch of ammonium, so you should keep these bacteria around. Like, if I ever make it really, really rich, I'm going to hire a sushi chef and make him live in my house. So I just come home and go, sushi, right now. That's what I would do every single day. Chop, chop! Shirashi. These, because they use a lot of ammonium, house bacteria to produce extra for them. Instead of just picking it up out of the dirt, they keep a production facility in the roots themselves. So some plants have the bacteria living in their roots. That's special to some plants. Now, this plant is going to use the ammonium to build amino acids. I told you this. Here comes some vocab. They suck it up out of the ground, uptake, to make it part of them. That's called assimilation. So this is vocab. Assimilation is when you make it part of you by uptake, which is soaking it out of the environment. Those are words you probably already knew, but just in case, assimilation is to make it part of you. Uptake is to drink it from the ground or whatever, to soak it up out of the environment. And most of you know that we eat our protein to build our own proteins. Since most of you know the amino acid thing, let me try something out for you. When I eat black beans, I'm not trying to be a black bean. I'm trying to be a handsome mofo. So for me, I don't need to build black bean proteins. I need to build sex appeal proteins. That's true, yeah, I'm pretty full, right? Yeah, thank you. In other words, the protein that you eat is not the protein that you need. We get rid of the stuff that we don't need, just keeping the ones that we need to assemble for us. You know, like cutting up a magazine to write a letter. You're going to throw away a whole bunch of letters because you're not going to say the same thing the magazine said. But side trip, Anybody know the perfect protein source? What could you eat and not have any wasted amino acids if you're trying to build a human? Another human. Absolutely. Because, you know, like, you look pretty humanish. So I'm guessing that, you know, you're like less attractive version of me. Like, you probably have most of the right ingredients to build human proteins. So I could probably cut that up and eat that, and that would probably be most of the stuff that I need to build me. But most of our diet has amino acids we don't need. So in our guts, we keep a colony of bacteria. Please look up. They're called digestive bacteria that just tear apart our diet proteins so we can absorb the amino acids we need for us and then get rid of the ones we don't need in poop.
So if you ate a human, you wouldn't poop?
Well, you would probably poop less amino acids. I think your poop would smell less. I think if you ate a human, you know, most of your poop is not stuff left over from your diet. You know, a tremendous amount of your poop is the dead microbes of your gut ecosystem.
Really?
So you'd pretty much poop no matter what. Yeah, like if I fed you vitamin pills, you'd still poop.
What does that mean?
Which part? The vitamin pills or the food?
Is there a significance to if we only ate vitamins we would still poop? I mean, that makes sense.
Not really.
It's a really gross question. Really gross.
I think we have a minute, but hurry.
Shark. What does that mean? Like, what does it mean? Like, what is it? Like, you poop or fart at the same time.
What?
Like, what? Like,
I think it means when you try to fart, but poop comes out? Is that what you're asking?
like, is that amino acids?
I feel like you knew this already.
No, I'm actually curious. Like, is it?
I think it just means that you probably need to hold that a little bit for like the liquids and the solids to rearrange, but you let it out too soon.
What is it?
I'd like to take this moment of YouTube broadcast to mention number one, I have no taboo. If you want to talk about poo, I can talk about poo. But B, I reserve the right to be the only funny guy here. Okay. I need to point something out about these digestive bacteria, though. You already knew about those digestive bacteria. You've all heard the story. What happens to a vegetarian or a vegan when they eat meat for the first time?
Their stomach, like
They get like gnarly gut rot. How many of you have heard this concept? I went 11 years without eating meat. And then the first time I ate meat, after those 11 years, I ate one of the largest steaks of my life. It was like the size of that box. Wow. It was like a manhole cover of pretty much rare steak.
Oh.
My poor grandmother, like I hadn't seen her in forever, and I was like, oh, thanks, I don't eat meat. She's like, well, it's okay, I'll just make you some chicken. And I was like, no, Grandma, nothing with eyes. And she's like, pigs have eyes, right? I was like, fish have eyes? She's like, so what do you eat? And I was like, you know, like beans, rice, pasta, sometimes some veggies. She's like, no, but what do you eat for food? And I was like, beans, rice, pasta, sometimes veggies. And she's like, how will you be a man? And I was like, I'm a man. And she was like, so I said, bucket, I'll eat the steak. And funny story, somehow I've never understood this. I was fine. I slept great, pooped great, ate great. It was awesome. But it is true. And you should use this story to always remember that in our gut we have all these bacteria that help us rearrange from our protein inputs to our protein that we build up to the amino acids that we dump. Please look up. There's a bacteria in the ground that helps us decompose amino acids. They break those down into ammonia. That's why poop is good fertilizer. Since poop has amino acids, you can sprinkle poop around a plant, and decomposing bacteria will tear up their amino acids to make ammonium, which is that same fertilizer the plant needed. Somebody asked me earlier about the little cycle. Check this out. There's one cycle that turns nitrogen to the atmosphere and back. But here's your little cycle. Once you have ammonium in the ground, you can build a plant, which can feed an animal, which can drop amino acids that can become ammonium straight back for the plant. This is the little cycle. You don't need the other parts of this picture as long as you have ammonium to the plant, to the animal, back to the ammonium in the ground, to the plant, to the animal, back to the ammonium. Okay. So that's the little nitrogen cycle. But that ammonium is useful to other bacteria. Please look up. Nitrifying bacteria do this thing called nitrification. They turn ammonium into nitrate, and there are denitrifying bacteria that turn nitrate into nitrogen gas. Remember, that's not their whole life, that's not their mission, that's just one of their inputs and one of their outputs. In the course of being this bacteria, they make that change in cycle. Has anybody here ever kept or currently have a marine aquarium, a saltwater aquarium? So if you've ever even looked at one, underneath saltwater aquariums, you often find this wacky filter that has like a pile of little black beads and the water pours over that, and then there's like a... Okay, the reason that you have that is so that you can provide an aerobic environment for these bacteria. The wet-dry filter, the whole point of being wet and dry is to have aerobic and anaerobic, so that you can do these two steps and the fish don't drown in their ammonium. You can tell you have too much ammonium because you'll get an algae bloom if they've been pooping in there for too long and you still haven't built up these bacteria. So the funny thing is, for people who have like aquariums or have kept aquaria, this is like really common and straightforward and everybody knows it. Because fish usually eat plant or protein and they poop and that makes ammonium and there's no other way for it to leave. So this is really simple for aquarists. For the rest of you, I'd like to do 3 laps of review. You can check your notes and make sure that you got all this. First lap, we can go through all the bacteria. So you know, gas permeates into the soil where nitrogen fixers make ammonium. That ammonium becomes part of a plant, becomes part of an animal, where digesters tear apart proteins into separate amino acids. The ones you don't use are decomposed back to ammonium. And this can get confusing. That ammonium could either be soaked up by a plant or be absorbed by aerobic nitrifying bacteria, making the nitrate that's eaten by anaerobic denitrifying bacteria. Those are all the bacteria in your drawing. If you want to discuss those transactions, you could say fixation, assimilation, digestion, ammonification, nitrification, denitrification. It's just a bunch of stuff to learn, and it feels really abstract and useless. But I'm terribly sorry it shows up on like every AP test. Honestly, aside from my life as an aquarist, I never do this except for the AP test. It's on every AP test. So it's one of the crappy parts you gotta learn about the basics of the planet. I have available for you 6 minutes to answer your questions. And we can talk about poop, but first I want to make sure that we're available for this.
It says the arrow pointing to the plant's leaves. It says to build AA.
Amino acids. What else? I'd like to help you. I don't remember question 20, but yeah, I assume so. Yeah. You could kind of assume yes. Technically, it's important to point out that most of our bodies are inside these perfectly sealed boxes that might survive a pretty long geologic stretch.
Right.
And that's not a ton of organic material.
Like a whole grid, would that be
You'd be shocked. That's just a few bodies for thousands of square feet of soil. What we're talking about is like, imagine a humongous mass ring. That might make a little deposit.
Where to live time.
Isn't there like a huge deposit, like if you said like it's
Oh yeah, whole regions of the ocean that all got covered up at once. Huge swamps, seafloor areas, or bays that had some really weird catastrophic change that locked it all up in rock. Pretty rare.
And it'd be like if like ecosystems, like if the sea or something.
One places where a lot of organics builds up, consider that in the San Juan Channel, we've got water that's like 4,000 steps deep. In those areas where stuff settles, you probably have some decomposers, but if all of a sudden there was some climactic change that covered that with sand, the entire bottom of the Santa Barbara Channel would have one huge layer. And then if you keep adding those over millions of years, so that the next layer and the next layer and the next layer, now you've got a good fossil fuel deposit of 300 million. I need your attention, Miller. He asked a question that I thought was really interesting. He got some pretty good enrichment. While some of you had a conversation that was irrelevant, this is the chaos that I need to avoid during these last couple minutes of class. That neighborhood of the class was much too loud. I do not offer you free time to have your conversations in class. That's not okay. Beat it. I'll see you all tomorrow.
Guys, we got a point of view.